Section: Introduction. In this section, we will discuss the advancements in the field of autonomous agents. Our focus is on creating systems that can work independently, make decisions, and carry out tasks with minimal human involvement. These agents are programmed to understand instructions, process information, make decisions, and take actions to achieve autonomy. The introduction of large language models, LLMs, has opened up new possibilities in agent development. Current LLMs have demonstrated strong capabilities in understanding instructions, reasoning, problem-solving, and interacting with humans and their environments. By leveraging these powerful LLMs, emerging LLM-based agents exhibit impressive task fulfillment abilities across various environments, from basic virtual assistants to more complex systems involving intricate problem-solving, planning, and reasoning. A notable example is a travel agent powered by an LLM, as shown in a specific scenario. When a user requests help with trip planning, the travel agent breaks down the task into manageable steps. It then follows these steps sequentially to book flights, reserve accommodations, handle payments, and update schedules based on user preferences. Throughout this process, the agent showcases its reasoning and decision-making skills, distinguishing it from conventional software limited to predefined functions. To execute such tasks, the agent must interact with both LLM services, e.g., understanding user preferences, selecting which tool to use, generating responses, and traditional operating system services, e.g., accessing storage, running software. As the number and complexity of agents grow, there is added pressure on the capabilities of LLMs and operating systems. Challenges include efficiently managing agent requests within limited LLM resources and addressing delays in LLM response generation due to lengthy contexts. To tackle these challenges, we introduce AIOS, an LLM agent operating system that isolates and combines LLM and OS functionalities. To manage conflicts between LLM-related tasks and other tasks, we propose an LLM-specific kernel that separates oxygen monosulfide-like responsibilities related to overseeing LLM agents and their resources. This kernel aims to enhance the coordination of LLM activities by segregating functions into distinct modules. These modules include the agent scheduler for prioritizing requests, the context manager for managing LLM generation status, the memory manager for short-term memory, the storage manager for long-term data storage, the tool manager for external API tool management, and the access manager for privacy and access control. The LLM kernel also provides an interface for agents to access these services seamlessly. Furthermore, we developed the AIOS SDK to simplify LLM system calls for agent developers. With the AIOS architecture, agents like the travel planner can combine LLM reasoning with OS-level actions to handle complex tasks effectively. This integration equips multiple LLM agents to tackle diverse tasks requiring reasoning, execution, and interaction with the physical world. Moving forward, we aim to enhance AIOS to support tighter agent world integration, smarter resource management, and safer multi-agent collaboration, making it a vital platform for developing and deploying complex LLM agents. Section Summary. In this section, we introduce the concept of autonomous agents that can operate independently, understand instructions, make decisions, and interact with users and environments. Leveraging large language models, LLMs, emergent LLM-based agents demonstrate strong task fulfillment abilities, as seen in the example of a travel agent organizing trips for users. To address challenges like resource management and task conflicts, we propose AIOS, an LLM agent operating system that segregates LLM and OS functionalities, providing modules for agent scheduling, context management, memory and storage management, tool and access management, enhancing the coordination of LLM-related activities and enabling complex tasks involving reasoning and interaction with the physical world. Section: Evolution of Operating Systems. In this section, we will discuss the evolution of operating systems, OS, from their basic forms to the complex systems we use today. Initially, operating systems helped connect user tasks with the inner workings of computer hardware. They progressed from simple batch processing to advanced techniques like time sharing and multitasking, making it easier to handle complex tasks. As time went on, operating systems became more modular, dividing tasks like process scheduling, memory management, and file system management for better efficiency. The introduction of graphical user interfaces, GUIs, like Macintosh, Windows, and GNOME made operating systems more user-friendly. The OS ecosystem also grew, providing developer tools and libraries to create and run applications smoothly within the OS environment, such as Android Studio, Xcode, and Cloud SDK. Nowadays, we are entering a new phase where intelligent operating systems are being developed. By incorporating large language models, LLMs, these advanced systems aim to improve communication between humans and machines, ushering in a new era of user-computer interaction. Large language model, LLM, based autonomous agents use natural language instructions to solve complex tasks. These agents can be categorized into single-agent systems and multi-agent systems. Single-agent systems employ a single LLM agent for tasks like travel planning, recommendations, and design. The agent breaks down tasks into steps, utilizing external tools as needed. Multi-agent systems involve multiple agents working together, either cooperatively or competitively, to solve problems. Our AIOS architecture consists of 3 layers: the application layer, the kernel layer, and the hardware layer. Each layer has specific responsibilities, with higher layers simplifying interactions with lower layers. The application layer is where agent applications are developed and deployed, using the AIOS SDK to streamline the development process. The kernel layer includes the OS kernel and the LLM kernel, each catering to different operations. The LLM kernel focuses on LLM-specific tasks like context management and agent scheduling, crucial for LLM-related activities within the AIOS framework. Our focus is on enhancing the LLM kernel while maintaining the existing OS kernel structure, with key modules like the LLM system call interface, agent scheduler, and memory manager ensuring efficient execution of agent applications. Section Summary. In this section, we summarize the evolution of operating systems from basic functionalities to complex, interactive systems like those with graphical user interfaces, GUIs, such as Macintosh and Windows. The progression includes advancements in process management, memory management, and file system management, leading to efficient and user-centric OS ecosystems like Android Studio and Xcode. Additionally, we introduce large language model, LLM, based autonomous agents, categorizing them into single-agent systems, SAS, and multi-agent systems, MAS, that leverage natural language instructions for complex task solving, with applications in various domains like travel planning and social simulations. Section: Hardware Layer. In this section, we will discuss the hardware layer, which consists of physical components like the CPU, GPU, memory, disk, and peripheral devices. It's important to note that the system calls of the LLM kernel do not directly interact with the hardware. Instead, they communicate with the operating system calls, which then manage the hardware resources. This indirect interaction provides a layer of abstraction and security, allowing the LLM kernel to utilize hardware capabilities without having to manage the hardware directly, thus maintaining the system's integrity and efficiency. Moving on to the AIOS implementation, we will provide an overview of the basic design and implementation of each module in the LLM kernel. We will then introduce the LLM system calls that include essential functions for each module. Lastly, we will explore the AIOS SDK, which aims to simplify the development process for agent developers. Next, let's talk about the agent scheduler. The agent scheduler is designed to efficiently manage agent requests. Imagine we have different agents labeled as A, B, and C, each with multiple execution steps. In a sequential execution setup, tasks from the same agent are processed in order, which can lead to longer waiting times for tasks queued later in the sequence. To optimize this process, the agent scheduler uses strategies like first in first out, FIFO, round robin, RR, and other scheduling algorithms. By executing tasks concurrently, the scheduler balances waiting time and turnaround time for each agent. Tasks from different agents are interleaved and executed in parallel, preventing a single agent from monopolizing resources and minimizing idle times. Now, let's discuss the context manager. This component handles the context provided to LLM and the generation process based on that context. It involves two main functions: context snapshot and restoration, and context window management. The context manager ensures that the state of LLM's generation process is preserved when tasks are suspended by the scheduler, allowing for accurate resumption once resources are available again. It also manages potential expansion of the context window to handle long contexts effectively without compromising information integrity. Lastly, we will touch on the memory manager. This module manages short-term memory within an agent's lifecycle, ensuring data is stored and accessible only when the agent is active. Each agent's memory is stored independently, with restricted access to other agents unless authorized by the access manager. More advanced memory mechanisms like shared memory pools or hierarchical caches can be integrated into AIOS in the future to enhance data retrieval and processing speed for user queries and interactions. Section Summary. The hardware layer consists of physical components like CPU, GPU, memory, disk, and peripheral devices, with the LLM kernel system calls interacting indirectly with hardware through the OS's system calls to maintain system integrity and efficiency. In this section, we provide an overview of the LLM kernel's design and implementation, introduce essential LLM system calls, and explore the AIOS SDK to aid agent developers. The agent scheduler optimizes task processing by employing scheduling algorithms like FIFO and round robin to balance waiting and turnaround times, ensuring efficient resource utilization and minimizing idle times. Section: Storage Manager. In this section, we are responsible for managing the long-term storage of data in the AIOS system. We ensure that information is stored securely using various durable mediums like local files, databases, and cloud solutions. This allows for data to be preserved for future reference or analysis. Additionally, we support the enhancement of agent knowledge and user experience by storing user preferences and interaction logs. Furthermore, we oversee a diverse set of API tools in the AIOS system through the Tool Manager. These tools, categorized into different groups such as web search, scientific computing, and image processing, enhance the functionality of LLMs. By integrating these tools, we enable agents to work with different types of input and output, aiding in their development within the AIOS environment. The Access Manager controls access permissions among different agents by managing privilege groups. Agents outside a specific group are restricted from accessing resources like interaction history. To ensure system transparency, we maintain detailed logs of access requests and activities to prevent potential security breaches. The LLM system call interface in the LLM kernel provides basic operation functions for agents. Similar to operating system calls, these functions include agent management, memory operations, and access control. The list of system calls can be expanded in the future to support additional operations. The AIOS SDK equips developers with tools to create advanced agent applications within the AIOS framework. This toolkit includes functionalities for agent initialization, lifecycle management, resource monitoring, and task planning. We continuously update and expand the SDK to meet the evolving needs of agent applications, aiming to empower developers to maximize the potential of their applications within AIOS. In our evaluation, we assess the correctness and performance of AIOS modules when multiple agents run concurrently. We investigate the consistency of LLM responses to agent requests and evaluate the performance of AIOS scheduling in balancing waiting and turnaround times compared to sequential execution. For our experiments, We use Python 3.9 with PyTorch 2.0.1 and CUDA 11.8 on an Ubuntu 22.04 machine with 8 NVIDIA RTX A5000 GPUs. We utilize publicly available LLMs as the foundation of AIOS and configure specialized agents for mathematical problem solving, narrative generation, and restaurant recommendations. These agents interact with the LLM backbone during execution. To analyze consistency, we run individual agents and then in parallel, comparing their outputs using BLEU and BERT scores as metrics. Both scores reaching 1.0 indicate perfect alignment between outputs in single-agent and multi-agent settings, affirming the effectiveness of our design in supporting concurrent operations. Section Summary. In this section, we discuss the key components of the AI operating system, AIOS, including the storage manager responsible for long-term data preservation, the tool manager that integrates various API tools to enhance LLM functionality, the access manager for orchestrating access control among agents, the LLM system call interface for basic LLM operations, and the AIOS SDK designed to empower developers in crafting sophisticated agent applications. We also evaluate the correctness and performance of AIOS modules when multiple agents run in parallel, ensuring consistency in responses and assessing scheduling improvements in balancing waiting and turnaround times. Section: Performance Analysis. In this section, we compared the efficiency of AIOS using FIFO scheduling with a non-scheduled approach where 3 agents run at the same time. In the non-scheduled setup, the agents follow a specific order: math agent, narrative agent, and rec agent. We used 2 measures to evaluate time efficiency: waiting time, from request submission to start, and turnaround time, from request submission to completion. Since each agent sends multiple requests to the LLM, we calculated the average waiting and turnaround times for all their requests. To reduce randomness, we ran these agents with and without scheduling in 5 trials. The results, as shown in the efficiency table, indicate that the non-scheduled approach works well for agents early in the sequence but leads to longer waiting and turnaround times for later agents. On the other hand, AIOS's scheduling effectively manages both waiting and turnaround times, especially beneficial for later agent requests, particularly with a large LLM. This highlights the importance of our scheduling method to handle multiple agents' parallel operations.